Okay guys, so today we'll do experiment 9, and it kind of piggybacks off of what we did last week with the experiment 8. If you recall, what we did last week is we ran a current through a coil, and then we generated a field in the coil, and then looked at the field, studied the field. Now what we'll do is kind of opposite thing, kind of, not exactly, but as it turns out, if you have a magnet, bar magnet, you can actually generate what they call this EMF, back EMF, some voltage, by inducing a change in flux. Now what is a change in flux? Well, flux, you can think of flux as just a measure, a count of how many things are cutting through a surface at some time, right? And so what I have here is a picture to kind of demonstrate this. So the procedure is going to be, we have a magnet, and we're going to drop the magnet from some starting position way above the solenoid, and then just drop it through the solenoid. So the 3 stages of the drop, when you let this thing go. So initially it's sitting, the magnet is sitting way up here, above the solenoid. This is my solenoid. The magnet's way up here. And then if I were to ask you what the flux is going through the solenoid at this instant, it would be 0. Why? Because the field lines are way up here. The solenoid is right down here, and breaking stuff. And so the number of lines cutting through the solenoid at this instant is 0. So the flux here is 0. And then once you drop it, it's going to be in free fall, and then at some point the magnet's going to be sitting in the solenoid like so. And at this point, all the lines are going through the solenoid. So there's a max flux, or the maximum amount of film is cutting through the solenoid at this line. Is what you'd have. So 0 flux initially, maximum flux at some point in the middle of the drop, and then at the end we have the magnet sitting way down here. The flux of the solenoid now is 0, and so we go from 0 flux to maximum flux to 0 flux again, right? And so what we have here is a change in flux, and this change in flux is going to induce a back EMF we'll talk about. But in essence, here we have a change from 0 to maximum. So this change is positive, right? 0 is some maximum value, so this delta phi here is positive, phi is flux. So delta phi is positive, so positive change in flux. And then in the second half of the drop, as its magnet's falling out of the solenoid, the change in flux is going to be negative. So it's going to go from some max value, it's going to decrease to 0. So change in flux here is positive, change in flux here is negative. That's going to be important when we study the graph, right? So now we're going to go over here and talk about this equation over here. So this is a Faraday's law, it's in your book. It says that the EMF, back EMF, the voltage you induce is proportional to this thing here. So we have negative N, which is just the number of turns in the solenoid. Remember we did the lab last week, we talked about N. So this is just the number, it's just a constant, 600 in our case, right, last week. And then we have this gradient, this rate of change, so delta phi over T. So this is the rate of change of flux over time. Right, so this is the rate of change. And then what we'll do here is we'll rearrange this guy. We'll move this dt to this side, for those of you who had calculus, move this to this side and integrate. And so now we have this function, epsilon dt. Integrate this guy gives you negative n, which is a constant, and this change in phi. Right? Now we know n is a constant, and this change in phi, if we go back here, so the change in phi is also constant. It's constant in the sense that the change going from here to here, this change here has to match the change going from here to here, right? So we go from 0 to some max value, and then from that max value to 0. So the change here has to match the change here, right? So this thing is a constant. Change in phi is a constant over this whole drop, right? And so we have this guy. Integrate this guy, we get this number here. And now for those of you who had calculus, know that this thing here is just the area under the curve. So for instance, if we have some function f of x dx integrated over some xi, initial x, some final x, if the function was some funny function like this, right? If you integrate this guy from some initial x to the final x, right, you get the area under this curve. So you get this number. It's just the area under this curve, right? Similarly here we have some function here that's some epsilon, or v in this case, as a function of time. if you integrate this guy, which is what we're doing over here, you get, it tells you get this constant over here. Now, negative n, which is the constant, and then a change in phi, right? Okay, so what this will allow us to do is to basically count the change in flux. What we want to verify is that the change in flux is the same for these two halves of the drop, right? And the way we'll do that is we'll, drop the magnet, plot a graph, which will look something like this, right? And then we'll try to get the area under the curve for each pulse. So we'll have two pulses, so we'll get the area under this curve here, and then get the area under this curve here. Now the area under the first pulse corresponds to the first half of the drop. You can see that the first pulse is positive, and this is just for this case. You'll see the first, and also it depends on the pole that you're dropping down, etc., etc. But in this case, we have the first pulse is positive, right? So this is up, and again, this is the graph is delta phi, not phi, but delta phi, so change in flux. So the change in flux for the first half of the drop is positive, which is why you have a positive pulse over here, and then the second half, change in flux is negative, which we have negative pulse. But what we said is that the change in flux here has to equal the change in flux here, right? So we know that, which means that the area under the curve, under this curve, has to be exactly equal to the area under this curve. Now what you'll notice is that this thing is not symmetric, so it should look kind of like what I've drawn on here. But anyway, so you'll have the second half of the second pulse will look squished compared to the first one. You have to make some. You have to discuss why that is, right? But in essence, what we'll do is that once we have our graph, we'll try to get the area under the curve here. And the way we'll do that is we'll use some kind of calculus, or a little bit almost. So what we'll do is that we'll break this thing down into a whole bunch of tiny trapezoids, right? Something like this, a whole bunch of them, right? And then we'll get an area for each tiny trapezoid as we go, and then add them all together, and then that's how we'll get the area under the curve. And so we'll do that for this first pulse, and then we'll do it for this second pulse, and then we'll compare the two, and we should get the same value, regardless of what the graph looks like, because we know that change in flux here has to match the change in flux here, right? And so that's basically it. Now let's go and see how the procedure goes.